All right. So today we're going to talk about determinants and the properties thereof. Determinants are one of those things that we've used a little bit with the two by two case. So this is going to be determinants for bigger matrices. Um, Word of caution right off the top. Caution. The determinant of a matrix A is only defined for square matrices. That's it. Don't try to tell me about the determinant of a matrix that's not square. We don't do that. That's not going to be a thing that works. So we're going to have a bunch of ways to calculate determinants, but they're all going to be on square matrices. So square is the name of the game here. Our three ways to calculate the determinant are going to be thing one, row reduce, and then multiply the pivots. One small issue with this is if row exchanges are required, each one flips the sign. So, row exchanges flip sign. So if you require two row exchanges, you're going to flip the sign twice. That's going to get you back to where you started. If you have one row exchange required, you're going to get negative the product of the pivots. Okay, that's going to be item one. This is actually how the computer does it because otherwise it's gross. Thing two is going to be we can use this thing called the big formula, which is in 5.2. Uh, it's real gross. This one's nasty. I would advise generally against that thing. You're going to have to use it occasionally, but it's not too bad. The other one is the cofactor formula or the cofactor expansion. Uh, this one's going to be what we're familiar with. You guys have actually used this thing before if you've calculated the cross product of two vectors. So think V cross W from Calc 3 if you've had that. If you haven't had Calc 3, don't worry about it. It's not very hard. So the cofactor formula is going to be the one that we kind of aim at most of the time. Um, that said, this first one is the one that the computer does. It's also relatively straightforward. So pick your poison. I'm gonna tend to do the cofactor if nobody gives me anything else. That's actually the thing we do with the two by two matrices. So in the two by two case, whoops, that's terrible handwriting, Joe. In the two by two case, this is the determinant of A, B, C, D is given by that thing we divide by in the inverse formula. So that's AD minus BC. Notice here, these look like absolute value bars. The determinant is kind of like an absolute value-ish thing. It doesn't act like it can be negative, so it's not actually an absolute value, but it kind of acts a little bit like the magnitude of vectors or like the absolute value of a scalar. So we use these kind of bars to indicate that this is a number that tells us something fundamental about our matrix. So in the two by two case, you already know how to calculate these. This is me actually kind of using the cofactor formula. Now, there's a whole bunch of properties. I'm gonna write I'm gonna write some of them down. That's really all that's in this section. So we're not really going to tell you how to calculate the determinant in here, other than to say that there's some properties. There's more of these than there need to be. So I'm going to put them out. I'll tell you which ones are the ones that determine the determinant. So thing one is the determinant of an identity matrix is one, regardless of the size of the identity matrix. Thing two, The determinant flips sign with row exchanges. That's just this thing we talked about here. So with just these two facts, you can tell me the determinant of a permutation matrix because you can tell me how many row exchanges were required to get that permutation matrix. That should be a callback to a homework problem that you did. In thing three here, we get part A and B, but the determinant is linear and yeah, in each row separately. So this is not quite a linear operator thing, but it feels quite a bit like one. So thing A for this is going to be something like the determinant of a matrix that has T times row one and then row two and then on and on down here to row n. This is going to be T times the determinant of this matrix, but without the T in it. So row one here, regular row one there, regular row two here, on down to regular ass row n at the bottom. So I can pull a T out of a row. The little consequence here, if you have a diagonal matrix, so let me just throw a little example in here before we get you too confused. So an example would be that if I'm calculating the determinant of the matrix that's twos and zeros, you might be a little inclined to say, oh, well, if I factor a two out of this, then it's the identity matrix. So there should be two times one, I should get two. That's not how this works. You get two times the determinant of this matrix, but I took a two out of just the first row. And then I'm going to take another two out of the other row. So I'm going to get a four out of this total. So that's what I mean by it's linear in each row. You have to factor from each row kind of separately. Cool that? Hopefully. All right. Three, part B here is going to be the determinant of a matrix where I've got, like, say, some rows, and then here I've got, like, uh, row I plus row I, but different. And then some more rows. So this is essentially, I've got regular rows, and then in this one spot, I've got two rows added together. This is going to be the determinant of the matrix with that regular row I in there, plus the determinant of this same matrix, but with row I prime in there. So essentially, I may have this case where if I've added a couple of rows together, I'm going to take the determinants of those matrices individually and add them to get the determinant of the sum. Hopefully that makes some sense. Okay. Then there's going to be more properties. These three properties here, so these ones are enough. So let's say here. This makes the determinant. All these other properties, so I'm going to give you like, yeah, seven more properties in my notes here. I'm going to give you seven more properties. They're all consequences of these first three. So let's go get seven more properties. So these are going to be kind of the bonus properties. So let's talk property four. So property four is if I've got row I equal to row J, right? So if I've got two equal rows, that implies the determinant of my matrix is zero. Okay, why would that be the case? Well, if they're equal, right, then I can kind of subtract and I can get a row of zeros in there. And then I can use this linearity property to say that that uh, is in fact a zero determinant because I can factor a zero out of it essentially. Which brings me to what in the book is property six. I really think this probably ought to be property four, but whatever. Um, property six is just if row I is equal to zero, then the determinant of our matrix is zero. Right. So a row of zeros makes a determinant of zero. That kind of tracks with what I'm thinking about this with respect to invertibility, right? Okay. Five is essentially saying that the determinant of a matrix A is the determinant of the row reduced version as long as I'm only applying elimination matrices, right? So this is none of that. I'm going to divide a row through by a number thing. This is just applying straight elimination matrices. Only EIJ matrices allowed. Right. I know I tend to, when I'm row reducing, I tend to divide rows through by stuff. Remember, in this case, you're not allowed to do that, right? This is only row reduction. Okay. Property seven. Uh, if my matrix is triangular, right, in either way, either lower or upper, that means it's already row reduced essentially. And then the determinant of my matrix is the product. This is like one of those sum things of the AIIs for I equals 1 to n. This is just a multiply down the diagonal. So this is the product of the diagonal entries. Okay, property 8 is going to be if the determinant of our matrix A isn't zero, this is equivalent to A is invertible. Remember, we're only talking about square matrices here, so this is where invertibility definitely makes sense. And looking at these guys, I can kind of see that four put together with maybe three, right? Like this thing about if the rows are equal, I'm going to get a determinant of zero. The, putting that together with three is probably going to tell me that linearly dependent rows are going to give me a zero. That's really the case. So if I have linearly dependent rows, I automatically get zero out of my determinant. That means I'm going to be not invertible, right? That means I'm going to be singular. So this is just the opposite case. So the opposite case there holds. I should probably write that down. Let's just throw that in here. Determinant of A equals zero is the same thing as A is singular. Okay. Item nine is the determinant of a product is actually what you would want it to be. It's the product of the determinants, which is real convenient. Um, this is kind of nasty to prove, so I'm just going to leave this here. Um, all right. And then 10 is that the determinant of A transpose is the determinant of A. That's going to be a very convenient fact for us. That's going to be something we use on the regular. So these are all the properties of a determinant. These are enough. So these first three are enough to uniquely determine to make it a determinant. So anything that obeys these three is just gonna be the determinant, which is kind of a weird thing to say, but that's like a surprisingly important part of linear algebra at higher levels, is just knowing that the determinant is unique and has these three properties. Otherwise, for you guys, I just want you to know that these properties exist and that they're going to be interesting for us. We're going to have these methods to calculate this thing. They're all going to be a little bit gross. Some books really like to lead the topic of linear algebra by determinants, and I really fundamentally don't because I think you should think of a matrix as a function fundamentally. And this determinant thing is a little bit is like, what is this telling me about the function? It's not real obvious. There are some good tie-ins there, but it's not incredibly obvious. So I'd rather have you think about a matrix as a function first. Um, that'll be it for this. We'll get around to calculating determinants in the next couple of videos.